This video contains solutions to practice problems from section 6.2 on properties of power series. So a lot of these problems are based on some work that we did in class developing some power series for some common functions. And one of the common functions that we found is that 1 over 1 minus x can be represented by the power series, the sum as n goes from 0 to infinity of x to the n, and that converges on the interval -1 to 1. So this comes from our knowledge of geometric series, but what it allows us to do is plug different things into that formula to get different power series for a given function, or as in this problem, interpret a given power series to figure out what function it represents. So in this case, we can take this series and rewrite it as the sum as n goes from 0 to infinity of x over 2 to the n, just using our rules of exponents. And so when we think about this series and how that compares to the series that we were given, we realize that all we did was plug x over 2 into our formula 1 over 1 minus x. And that's going to converge when the value of x over 2, absolute value, is less than 1. Remember, this interval here can be thought of as absolute value of x less than 1. So whatever we plug into this formula, its absolute value has to be less than 1. And so the convergence, if I multiply both sides by 2, this is going to give us the interval absolute value of x less than 2, or in other words, -2 to 2. So that's my interval of convergence. And optionally, I can clean up this formula, right? So I can take this formula and multiply both top and bottom by 2 and rewrite this as 2 over 2 minus x. But that's the function that we're talking about, and there's our interval of convergence. So similar setup here. Again, what we're thinking about is this looks a lot like our formula 1 over 1 minus x equals the sum as n goes from 0 to infinity of x to the n, except instead of x to the n on the top of our fraction, we've got x to the n on the bottom of our fraction. But that's not a big deal, because all we're really doing here is we're saying that we've got the sum of 1 over x to the n power. Now, crucially here, we do have another difference, and it's easy to miss this, but this sum starts at 1, whereas our given sum starts at 0. So what are we missing here? Well, what we're really thinking about is we want to take the sum as n goes from 0 to infinity, because this is going to be our function 1 over 1 minus 1 over x, because that's this series. But then we have to subtract the 0 term, because we don't actually have that term, because our given series starts at 1. So the 0 term is 1 over x to the 0 power, which is going to be 1. So we're just subtracting the number 1 here, and that adjusts the sum so that it actually starts at 1, like the one that we were given. So our function is 1 over 1 minus 1 over x minus 1. Lots of 1s, and it looks a little weird. Again, we can clean it up if we want to. And the interval of convergence here is going to be where the thing that we plugged in, its absolute value is less than 1. Right? It's not just absolute value of x less than 1, it's whatever we plugged in, that absolute value has to be less than 1. So if I multiply both sides by the absolute value of x, what I get is that the absolute value of x is greater than 1. So actually this series converges from minus infinity to minus 1, or from 1 to infinity. That's my interval of convergence for this one. And if I do some algebra here and clean this up, this works out to be 1 over x minus 1, and gives me a slightly different looking series for that function. All right, a couple more of these. So again, here the difference is this looks a lot like the one that we just did, except instead of having all of the powers of x starting at 1, we've only got the odd ones. So we're going to have to do a little bit of manipulation here, but we can do it. So first things first, we want to understand that we can split off one copy of 1 over x. So I'm going to write this as 1 over x times 1 over x to the 2n. And that 1 over x, remember, as n is concerned, x is a constant. So I can pull that out of my sum. And then 1 over x to the 2n, I'm going to think of that as 1 over x squared raised to the n. So now this looks like my series. Remember, the series that I'm always kind of be keeping in the back of my mind is that if I sum x to the n, then I get 1 over 1 minus x. So here I'm summing 1 over x squared to the n, so I'm going to get 1 over 1 minus x, 1 over x squared. And the interval of convergence here is when the thing that I plugged in, remember it's not just x, but when the thing that I plugged in, when its absolute value is less than 1. So multiplying both sides by the absolute value of x squared, which is just the same as x squared, because x squared is always non-negative, we get x squared greater than 1. So where is x squared greater than 1? Well, we can think about this graphically. Here's y equals x squared. Here's y equals 1. And so what we want to know is, when is my x squared function greater than 1? Well, that's going to be from this point to the right and from this point to the left. Well, this point is positive 1 and this point is negative 1 because that's where x squared equals positive 1. And so again, here our interval is minus infinity to minus 1 or 1 to infinity. So same interval as the last one. And again, we can do some algebra here to clean up our function. This one works out to be x over x squared minus 1. So that's the function that we're representing, and that's the interval of convergence. All right, one more of these and then we'll move on to a different type of problem. So this one we don't have an actual sigma formula for because the pattern is a little bit more complicated, but we can still relate this to what we know. So what we're seeing here is what looks a lot like the series that we're used to, which is the sum as n goes from 1 to infinity of x to the n. And actually, because that would require an adjustment, let's just go ahead and start at 0 and then think about what the adjustment would have to be. So this is 1 plus x squared plus x cubed plus. But now what happened was a couple things. First, we're missing the 1, right? So we have to subtract 1. And then the other thing that's wrong is that all of the multiples of 3 powers, those are the ones that have my minus signs. So instead of adding x cubed, I'm subtracting x cubed. Instead of adding x to the 6th, I'm subtracting x to the 6th. So it looks like I'm subtracting the multiples of 3 powers, which I can do by subtracting x cubed to the n, because that will actually subtract off the powers that I'm missing here. But if I leave it like this, then what would happen is the multiples of 3 powers would just cancel out and they would be missing from this sum. And that's not what I'm seeing here. I'm seeing them there with a negative sign, which means I actually need to subtract them twice, once to cancel them out, and the second time to bring them back in, but with a minus sign in front. Now, one slight problem here, this sum, because it starts at 0, includes the number 1. And so actually I would have minus 3 here. So I need to get rid of this minus 1. Now the 0 term in my first sum is getting subtracted twice. So I'm going to have a negative 1. So now I need to adjust that and bring it back in as a plus 1. So that way I don't have any constant term here because of the plus 1 and the minus 2. Okay, let's put this all together now. So the first sum, that's 1 over 1 minus x. That's our familiar series. Then we've got a plus 1. And then we've got minus 2 times 1 over 1 minus x cubed, because that's what I'm plugging into that series. And again, we could do some algebra to clean this up, but let's just leave it like that for now. Now, what's my interval of convergence? Well, I plugged into my series twice, which means the interval of convergence of this series is the overlap of the intervals of convergence of the two things that I plugged into. This will only be true, this equation will only be true if both series on the left converge. So the first one, we know what the interval of convergence there is. That's absolute value of x less than 1. The interval of convergence here, that's going to be absolute value of x cubed less than 1. Now, when is that going to happen? Well, again, I can think about this graphically. Here's what y equals x cubed looks like. Since the absolute value has to be less than 1, what has to happen is the y value here has to be between y equals negative 1 and y equals positive 1. But this point here is positive 1. This point here is negative 1. And so again, what we can see is that my x has to be between minus 1 and 1. So both series have the same interval of convergence, minus 1 to 1. And so that's my interval of convergence for this series. So there's my function, and there's my interval of convergence. For this problem, we're being asked to find a power series representation of the function f of x equals natural log of 1 minus x squared, and we want to find the interval of convergence. So what we learned in class is that we have a power series representation for the natural log of 1 plus x, and this looks like the sum as n goes from 1 to infinity of minus 1 to the n plus 1 multiplied by x to the n divided by n. We got that by integrating a version of our geometric series. And the interval for this series, the interval of convergence, is that the absolute value of x needs to be less than 1. So for our function, which is the natural log of 1 minus x squared, what we're going to do is substitute x squared in for the x in the previous series. So that gives us negative x squared to the n over n, because we're going to think of this as natural log of 1 plus negative x squared. So we're plugging in negative x squared. And so we can simplify this a little bit. This gives us n equals 1 to infinity of negative 1 to the n plus 1. And then we've got negative 1 to the n multiplied by x squared to the n, or is it just x to the 2n? And now we've got two copies of a -1 exponential term. So if we think about that, combining those is going to give us -1 to the 2n plus 1. But 2n plus 1 is always an odd number. When n is 1, that's going to be 3. When n is 2, that's 5. n equals 3 gives us a 7 power there. So that's always just going to be -1. -1 to an odd power is always going to be -1. And so this is just -1 with no exponent, right? Because it's just always going to be -1 multiplied by x to the 2n divided by n. So there's our power series. What's our interval of convergence? The interval of convergence of this series would be when the absolute value of the thing we plugged in, right? So this x here, this represents this x. But our series doesn't have an x there. It's got a -x squared there. So for our series, the absolute value of -x squared needs to be less than 1. That's the same as x squared being less than 1. And if we think about the graph of y equals x squared, that's going to tell us that x here has to be between -1 and 1, because that's when our parabola here is less than y equals 1. And so that's going to give us -1 to 1 as our interval of convergence. So this time we're being asked for a power series representation of an integral. In this case, we're integrating the natural log of 1 plus x squared. And so what we're going to do is find a power series for the thing that we're integrating, and then we're going to integrate that power series term by term. So the first thing we're going to do is find a power series representation for the natural log of 1 plus x squared. So based on what we saw in the previous problem, we're going to use our power series representation for the natural log of 1 plus x. And so this is going to give us -1 to the n plus 1. And then we're plugging in x squared here. So we're going to get x squared to the n divided by n. So that's going to give us the sum n equals 1 to infinity, -1 to the n plus 1, x to the 2n divided by n. And our interval of convergence here is when the absolute value of the thing we plugged in is less than 1. But that, again, just like on the previous slide, is going to give us -1 to 1. Now we're going to integrate. So when we integrate this, the integral of the natural log of 1 plus x squared, we're going to get a constant, which we're going to put in front because we kind of think of that as the x to the 0 term. And then we're going to integrate each of these terms in our series. So we're still going to have a -1 to the n plus 1 because that doesn't have any x's in it. We integrate x to the 2n, we get x to the 2n plus 1, just using our power rule, divided by 2n plus 1. But then we already had a factor of n in the bottom there. And so this is our power series representation for our integral. And we leave the plus c there because we did an indefinite integral, and so we always have a plus c when we do that. But now what's the interval of convergence? The interval of convergence for this series is still going to be -1 to 1, but when we integrate or take a derivative, the interval at the endpoints can change. So it could converge when it didn't converge before, or vice versa. So let's see what we get. So we got to plug in x equals 1 and see what we get. We're going to get the sum. We're going to ignore the c because that's not going to affect whether or not this series converges. So we're looking at the series part of it, sum 0 to infinity, -1 to the n plus 1. When we plug in x equals 1, that x to the 2n plus 1 just becomes 1. Because 1 to the 2n plus 1 is just always going to be 1. And on the bottom there, I have 2n squared plus n, if I multiply that out. Now, this series absolutely converges. If we take the absolute value, that's going to get rid of the alternating sign, and then we just have 1 over 2n squared plus n. We can do a comparison of that with 1 over n squared, which we know is a convergent p series with p equals 2. So this absolutely converges. And then if we let x equal -1, we're going to get something very similar. We get the sum as n goes from 1 to infinity, -1 to the n plus 1. We're plugging in -1 for x, so we get -1 to the 2n plus 1. And then again, we still have 2n squared plus n on the bottom. And again, if we take the absolute value, all of those -1s will go away, and we get a series that converges by comparison with a p series. So this also absolutely converges. And so the interval of convergence for this series is the closed interval from -1 to 1. So again, when you take an integral or a derivative, the behavior at the endpoints is allowed to change, and in this case, it did change. Now, one more problem. So again, a different one that we talked about in class was that the inverse tangent of x, which we got by integrating a series for 1 over 1 plus x squared, can be looked at as a series, as the series n goes from 0 to infinity of -1 to the n, x to the 2n plus 1 divided by 2n plus 1. And then again, that converges on the interval from -1 to 1. That's a very common interval of convergence for these kinds of series, although some other series that we're going to see in the future are going to have different intervals of convergence, but we'll see that in the next section. So how do we find the inverse tangent of x cubed? Well, again, it's what we've been doing, right? We're going to take that series and we're going to plug in an x cubed. So that's going to be the sum n equals 0 to infinity, -1 to the n, x cubed to the 2n plus 1 divided by 2n plus 1. We can clean that up if we want to. That's going to be -1 to the n, x to the 6n plus 3 divided by 2n plus 1. What's my interval of convergence? Well, the absolute value of x cubed would have to be less than 1, and as we've seen before, that means the absolute value of x would have to be less than 1. So there's my interval of convergence, and here's my series.